example how we can design observer for a system where some state is not available for measurement. So we'll design this concept based on the theoretical foundation we have in the last lecture. So let's set the problem. We have system x not equal to x plus bu and y equal to cx, where A matrix is given to us -3, 8, 0, 0, and B matrix 0, 4, and C matrix 1, 0. And if you write the system in state equation form and output equation form, we have x1 dot equal to -3 x1 plus 8 x2, and x2 dot equal to 4 for u. And this is the state equation. And output equation y equal to x1, right? This is the x1. This is output equation. And here, if you notice in this equation, x2, there is no x2 component in output equation, right? Only y is equal to x1, only the function of x1. So we can write here, since x2 is not available in the measurement, so we need to design state observer. We need to design state observer to observe x2. To solve this, first we assume that all states are available. So first we are assume all states are available. First assumption for feedback. And design state feedback gains to meet the closed loop performance. So based on this assumption, design a state feedback control to meet the closed loop performance. Okay. Here we are assuming for designing the state feedback here, we are assuming the closed loop performance. Assume the desired closed loop performance as following characteristic. So where we are having the natural frequency omega n equal to 25 radian per second and damping ratio 0.707. So using these parameters, using these given parameters, we can form a characteristic equation. So using these, we can find the second order standard characteristic equation 2 zeta omega n s plus omega n squared. And if you substitute the above parameters in this equation, we have, we can write s squared plus 35 is 35.35 is plus 625 equal to 0. Okay, this is the desired characteristic equation given to us. Now, this characteristic equation given to us for finding the gain of the state feedback control, right? So let us define this equation. Based on these values, so based on this, okay. Now we'll find the characteristic equation for the given system. So this is the procedure we have followed before, how to find the gain of the system. So we have the desired characteristic equation and we have the system characteristic equation. So there we can find Si minus A matrix equal to 0. No, it is wrong. It should be Si A minus Bk equal to 0. So here K is basically K1, K2 matrix. So if you compare this equation and this equation, and we can find the control gain parameters, controller gain matrix, we are having K1 equal to, we can write K equal to, we found to be 16.5. We are not doing this. So this is already we have done. Please follow the procedure, what you have done, find the controller gain matrix. So you have to just compare the equation 1 and equation 2. You have to compare the coefficient of SS for both the equation and you can find the K1, K2. This is K1 and this is K2. Right. So this is basically the state feedback control algorithm. So here our state feedback control algorithm is equal to minus K1 x1, K2 x2, right? And here K1 is 62.5 x1, K2 is 8.09 x2. So if you notice here in the control algorithm, we are having x2. But as for the system given to us, in the output equation, only we have x1. So we need to design the observer here. So before proceed to the observer part, first we have to test the observability matrix, whether it is full rank or not. If it is full rank, then we can say that we can design the observer for this particular system. So since this is second order system, we can find the observability matrix, n equal to, so we can go till second term C transpose, A transpose, and C transpose, right? So here C transpose you can easily find. Let's find the second term, A transpose, C transpose. So this is for A transpose, we have -3, 0, 8, and 0. And for C transpose, it will be 1, 0. So the final vector, we are getting -3 and 8. Now, in matrix, you can form C transpose 1, 0, and A transpose C transpose, we have -3 and 8. Right. Now, if you find that, so there is two ways you can find that whether the system is observed or not. One is we can find the determinant and it found to be 8 and not equal to 0, it is a full rank. And another is rank. If you find the rank of n, it is comes out to be 2. So both the condition is satisfying, so system is observable. Hence, system is observable. Okay. So now we'll find the characteristic equation of the system, error system. So we know our observer dynamics from the observative mathematical formulation of the observer design, we have the error dynamics E naught dot equal to E naught E naught. So where E naught we had E minus LC, right? So this is the error dynamics we found in the last lecture. So if you can make E to 0, then we can say the all states are available for designing the controller. If you can make E not to 0 as time tends to infinity. So for this, we have to find the characteristic equation of the aerodynamics. Sorry, of the aerodynamics. So here we can find the characteristic equation of, this is the equation. Let's assume. So A naught we get lambda I, we can write lambda I minus lambda are the eigenvalues E minus LC equal to 0, and we can substitute lambda 0, 0 lambda, and we are having here we can write -3, 8, 0, 0, and minus L1, L2, the observer gains, and 1, 0. And so this is equal to 0, right? So we can further simplify. So we are getting lambda 0, 0 lambda -3, 8, 0, 0, and minus L1, 0, L2, 0 equal to 0. From this, we can further write lambda 0, 0 lambda minus 3 minus L1, 8 minus L2, 0 equal to 0. And finally, we have lambda plus 3 plus L1 minus 8 L2 lambda equal to 0. And the characteristic equation we are having lambda square plus 3 lambda plus L1 lambda plus 8 L2 equal to 0. And also we can write in more simplified form lambda square plus 3 plus L1 lambda plus 8 L2 equal to 0. Right. This is the characteristic equation of the aerodynamics. Okay. So let us define this equation number 3. Okay. So now, as we have mentioned in the earlier lecture, that the eigenvalues of the observer should be faster than the eigenvalues of the digital system dynamics. So before that, we need to find the eigenvalues of our digital polynomial for feedback control design. So we have the digital polynomial for the feedback design. This is the equation we are having. Right, this is the digital dynamics we are having for state feedback control design. So let's work on this and find the eigen values or the poles of the characteristic equation. So given digital dynamics, given digital dynamics for state feedback control, we are having s squared plus 35.35 s plus 6 to 5 equal to 0. And from this, we can find S1, there is signal system that there are two poles, minus 17.68 plus minus 17.68i. So this is from the poles location, it is quite clear that the system is stable, right? So there is oscillation initially, but over time it will be decay to 0 because since this is the stable system, all poles in the left hand side. But as per the observer design, what you have learned that the observer must be faster than the system being controlled. Here we assume observer roots are 4 times as large as digit closed loop performance, right? This is already we had in the last lecture. So now 4 times of these roots, right? So we can find the observer roots the 1 and 2 OBS observer 4 into minus 17.68 plus minus 17.68 I. Okay, and this comes out to be minus 70.72 plus minus 70.72 I. And the characteristic equation we can find for the observer, we can find lambda minus lambda 1 OBS and lambda minus lambda 1, lambda 2 OBS equal to 0. And from this, if you substitute these values, one value is here, another value is here. So if you substitute and if you find the equation, we are having lambda squared plus 141.44 lambda plus 1 10003 equal to 0. Okay. Yeah. So now we can, this is the, so now what we'll do is this equation 4. Now we'll compare equation 4 and equation 3 to get the values of lambda 1 and lambda 1 and lambda 2. Right. So both the characteristic equation we have. So now comparing coefficients of equation 3 and 4, we have 3 plus L1 equal to 141.44, and from this we are getting L1 equal to 138.44, and 8L2 equal to 10003, and from this we can find L2 equal to 125037. Right. So this is the observer gain matrix. With these observer gains, observer error dynamics goes to 0. So if you do the MATLAB simulation with this observer, with these observer gains, observer error dynamics, which is E dot equal to A naught E goes to 0 as t tends to infinity. So you can say E goes to 0 as t goes to infinity. So this is how we can validate that all states are available, even they are not measurable in the output, but states are available to get the controller for the system. So this is very, very important part, how we can find the state which is not available in the output equation, but we can find the estimation of the state which is not available in the output equation for designing control. So let's stop it here. We will continue from the next lecture, how we can find the gain matrix. Because as of now, if you look whatever the controller methods we have designed as of now, we are assuming some desired dynamics, and also we are finding the characteristic equation of the system, and we are comparing both the equations, and we are finding the controller gains. But there are other ways also we can find the controller gain parameters without assuming the desired dynamics. From the next lectures onwards, we will have some controller concept, other way to define the controller, and we will go step by step. Thank you.